I think this is what, third talk I've given here? And it's always the toughest talk. And the reason it is that I deal primarily in abstract math. And for the first two talks, I didn't know what architect was other than the person who helped me remodel my kitchen. And I've become more sophisticated in that. And that's why I choose this word, right? The architect of matter. And I want to start by really getting to the soul of this entire talk. I mean neither. Right? I'm not going to read it to you, but the essence is, if you can prove A is less than or equal to B, or A is greater than or equal to B, this is the point. A is equal to B. And the reason she said that was because she was the first woman who was allowed to go to graduate school in Germany. And she thought they should have equal access to information. Right? She also was the mentor of Albert Einstein and has some profound work on geometry and symmetries. Right? We're going to be talking about architecture. This is Nick Rich, architect, where he uses light to create changes in space and time, to create different emotional effects, different type of architecture, as you were. And the last one is really Frank Lloyd Wright. Every time you have a new material, you really have to figure out what the core is, the nature of that material, if you want to use it to the maximum benefit. Physicists would say if you want to be in the geodesic. So, today I'm going to talk about architecture and creation of boundaries, dynamic property sets and their potential utility. Then I'm going to go into the geometries of light. Noether's theorem, what that means, how you can restructure some boundaries, how you can form knotted forms of energy, which lead to new property sets. Tying of knots. Notice I don't say property engineering here, I say property manufacture. And that's a key distinction. Right? I'm going to show you stuff that is certainly property engineering. I'm going to show you things that are definitively property manufacture. Right? And then path forward. What does that mean in terms of integratability and sustainability? And I begin with Newton's first work. Right? That if you start imagining new fields, new mathematical constructs, you can find other things with really trivial pieces of machinery. Glass in a geometric form. And that's what we've done. What we found is that we can take the periodic table and extend it by understanding what the empty space looks like in atoms, and using a set of mathematical transforms to manipulate that space so they have new properties. So, a slide from my second talk, where I was trying to figure out what architecture really was. These are the common forms, right? And I threw in the Vinci's just to open it up a little bit, but then to sort of shift into different forms of physics and mathematical constructs in the system. So looking at the coherent forms in rainbows, coherent forms in complex planes, and how we might look for coherent forms in the periodic table that I would consider two-dimensional, you might be able to extend that, or coherent forms in the universe in general. This is the one that I like the best, though. There's actually a SPA, the creation of space. Because that's what it's really all about to me, right? And the creation of space through the use of boundaries, right? So historically, and I brought, in preparation, I brought this book, 100 Greatest Discoveries in Architecture, according to somebody, right? But as you look through it, it's a lot like looking through the Nobel Prize. There's a lot of prizes given for new instruments. There's a lot of discoveries there that are based on materials. So you talk about bricks, I'm just going to zip through them, right? How they're used, modern frames, steel structures. Same thing for concrete, right? New forms on concrete. And then glass, right? How do we bring all of these together for new environmental effects, new energy effects, new emotional effects, right? In those systems. So really, creation of space through these boundaries. That's what I'm going to be talking about, except we're going to expand the definition of space in the mathematical context. And the second part of this book is about new integrations. So the very first one is a fireplace in a home. so that you can now have controlled environments inside as opposed to outside. So new integration, so servant-served spaces. Servants are the elevators, the infrastructure. The served are where you sit at a desk or live or those sorts of things. You have the same thing in bigness, where you're trying to integrate all of these, maybe the preamble to sustainable village or community design, which is a continuous feature. Today you can look at the mathematics behind that, trying to approach delta S equal to 0. Keyword is approach it. I think that's going to become really important in the future. And then lastly, new materials. New materials for new purposes. You know, rain cladding. I was just at Cornell. I used to have a much more fancy picture. I took this with my iPhone. But I was talking to a leading mathematician in abstract math and how we convert some of these things, because the difficulty with the brand new ideas, there isn't a lot of language that other people understand. So, dynamic property sets. So having an instant, Mark used the word instantiation, having an instant of something that you want to instantiate. Much like hitting a golf ball, I put a golf club in your hand. How do we do that? And a lot of different types of properties. Right? I'm not going to go into them, but I'm going to sum it up by one in nature. Right? And I would argue that all of these are probably things that eventually you'd like to invoke in a design of a new space. This is, these right here are eggs of a tree frog. Has a gestation period of 6 weeks. If a predator comes within the eggs within 3 weeks of its final gestation, it can instantaneously hatch. Right? If a school of fish comes underneath, they can delay it up to 3 weeks. Right? This is a hard polymeric structure. They've analyzed the frog right here. They've analyzed the tadpoles that come out under the quote instantaneous hatching, and according to the biological techniques they have, they look identical to those that have hit the full gestation. And what they found is that if a predator like a wasp comes here, just those eggs, which are going to be eaten by the wasp, drop into the water. If a snake comes on board, the entire leaf goes forward, and a school of fish, then it sort of delays. And you can get on the web and get an actual video. This was the one I thought was the least disgusting. And you can watch tadpoles jumping out of a snake's mouth. I mean, I won't argue what instantaneous means, but what's happening here is this hard polymeric structure is becoming fluid, and it becomes fluid like that, right? And they drop down. The author said, these fields are difficult to perceive and very likely difficult to conceive. And they've done, this video was done about, I think 7, 8 years ago. They've ruled out a lot of things. They've ruled out vibration, they've ruled out temperature, they've ruled out certain forms of electromagnetic fields. They can reproduce it with very, very narrow parts of the electromagnetic spectrum. Geometries of light. Fields, waves, and matter. I think these are all the same. I think they're recursive constructs. So before we get into it, let's talk about what a geometry means. This is one you're probably the most familiar with. Euclidean, you have a set of axioms, all right? And from those axioms, you try to deduce new properties. Let's look at these axioms in a slightly different way. These, let's look at these as definitions. Let's look at these as equivalencies for integration. And then let's look at an integration piece. That's going to become important. So, we know that Euclid, if we just look at how it's moved, right? Euclid started with the five postulates. Descartes introducing coordinate systems, right? So now much more precise, started moving into calculation with numbers as opposed to just symbols. Then we moved, so still in the Euclidean plane, right? Precursor to calculus, obviously. Then you moved into the non-Euclidean geometries, curved space geometries. Really the geometries of Poincaré, Gauss, and Riemann, right? Which led to Einstein's great discovery, right? And it was all because for a long time people tried to disprove the necessity of the fifth postulate, which could be equally argued on the sum of the angles. Then Klein started looking at symmetries and said, symmetry is the key thing in geometries. And then ultimately, they moved into the work that I do, topology, where you're looking at invariance as certain objects. So if I take a piece of rubber and put a hole in it, no matter how much you stretch it, bend it, fold it, it still has a hole, right? So coffee cups in a tori is viewed as really the same. So back to Emmy, right? What she showed is that for every symmetry, there's a conserved quantity, right? So she takes a Laplacian, which looks at motion, and she looks at an arbitrary coordinate system, and she says, hey, if I get that to be a constant, that means it's invariant over the whole system, and that means something is being conserved. Nobody really quite understood what that meant, which is why she was the most famous mathematician you ever heard of. And from run, cut, and Laplace, they put it in terms that physicists could understand, with momentums and angular momentums, etc. And lo and behold, these symmetries led to things that everybody in this class probably knows, right? So, invariance with respect to translation, conservation of linear momentum. Rotation, angular momentum, time, energy, Gauss transformations, electric charge. A really big deal. Huge. And just to underscore it, if you've been on the web recently, they call this the amplihedron, right? We'll get to that in a second. So, natural geometry. Notice how I've shifted here. From geometries to natural geometries. Those geometries which are indigenous to the form of the species. It's like looking at a problem and understanding the language of the problem. Once you understand the language of the problem, I think it was Socrates said, it's half solved, right? They help us understand the equations of motion compactly, that means fully and holistically. Faithful, just like your partner, they allow you to understand more of the laws of physics, right, without corruption. And that means you can find new symmetries, new conservation laws, new product, right? So geometries give us symmetries, and symmetries give us the conserved quantities. So back to the amplihedron. So in the 30s, sort of the quantum mechanics was just getting some wind behind it, and people were trying to do calculations on particle interactions. And it took the best people at MIT and Harvard a long time to do trivial calculations. Or a long time might be two groups of graduate students, a couple months, right? Then in the 60s, Feynman came out with his famous diagrams, which expressed it more in a geometric form. Now, engineers can start doing calculations. I don't know why they want to, but they could, right? And larger, more complex computations became available. In using those methods, they designed what the interactions were going to be in something like the circular. It took them 2 years to do that calculation with modern machinery. What a fellow has discovered at Princeton is that there is a geometric object as the core of quantum theory, and that object controls completely all the interactions. So, the comment is that those 2 years of calculations for the super collider can now be done by anyone in this class in an afternoon. Just by looking at, you guys are experts at that, at a geometry and how the geometry shifts. So you don't need to know anything about it. It's a lot like pouring water. Water is going to go downhill, right? So as long as you design the geometry for it to go downhill, it's going to go where you are. You don't need to solve those equations. Really a big deal, right? So that's the key. Geometry enables better understanding. So this is where we are, right? We know that in physics, right, geometry is a big deal. This is the key phrase. Electromagnetic fields determine the metric structure of space-time. That means how light moves over here determines what that structure looks like. Some abstract identities will tell you that you can collapse all this stuff into two equations for maximum and reproduce everything. So the conjecture is, not only does light have structure that determines this metric structure, but it has substructures. And that if you can modify those substructures, I can modify the spacing. And if I can modify that spacing, this is a light cone, then that particle which exists in the present, I can change what it experiences. All by changing out a connector, just like with a Lego block or anything. If I change a connector from an in and out to a tetrahedron or to something more abstract, I can change how these propagate, what type of networks I can do. So the big finding, light forms this boundary in space-time. In a very sophisticated level, it's a masket boundary, and it tells you how these are going to be matched, which tells you how it's going to move through the system, which means you can engineer the metric. If you know that, and you know that these structures are recursive, you could use any light to make these changes. I typically use visible light because they're easy to get and it's cheap. I can do much of the stuff I'll show you today. And if you knew what to do, you could buy the lights at Home Depot. The last is that once I have this plane, once I've changed this metric, I need to get it here to where I can see it, physically touch it. That means I need to invert it. And then lastly, properties are controlled by how I orientate those connectors. Right? So if I want to start shifting the properties, I'm going to start shifting the spacing. So what we do is we look at, to now try to categorize them, catalog them, and control them to a set of expectations, right? Because you want a material to be harder, you don't want it to turn translucent all of a sudden, you like to know what you're doing. So we take orbitals and we deform them. So a conformal map means you know exactly what A is going to go to B. Everything is preserved. Quasi-conformal means you got it good enough, right? And that's what we do. We deform it, and then through these deformations, we create new interactions in those two systems. So we go from standard copper into a deformed piece of copper. And depending on what connectors I use or what boundary conditions I use, it tells you how it's going to propagate and interact. This is the principle. So what does that boundary look like? So we have a way, I call this a traverse, of decomposing space-time into different properties so I can match it. And then I'm going to create this boundary, right? That's the same boundary as right here. Same boundary right there, called a limit set, right? Kind of, sort of, it's this, but not really. It's this when you put a lot of them together, right? So that's what you're looking at. Keep that picture in mind. Oops. So what I'm doing is I'm decomposing a fiber, which I'll just call F1, a function F1, that's above, and I'm matching it to something below, right? Where this is the present, right there. So you can think of this as above and this is below. This is the way they did it. And the boundary is what when I invert it, I'm going to experience. So I'm trying to make a new boundary, right? By taking the old metric structure and connecting it to create a new limit set. Now look at what's happening here, right? The mathematicians would call them dendrites, the mineralogists would call them dendrites. Other people call them other things. But these are fractal and they expand, right? So now I have two structures that are matched. On the quasi-conformal means not in the present, just a little bit above the present, a little bit below the present, right? And I match these, and as I match them, this boundary becomes more and more rigid. So the classic example is I take a dance floor, and I put Fred Astaire and Ginger Rogers there. They have an infinite number of moves they can make through the floor. And as soon as I put all of us in there too, they have a lot fewer moves that they can make. They might have infinite moves, but their orbit is highly limited, right? That's what we're doing right here. We're packing this out. It's called a space-filling curve, so that this orbit becomes very, very, very well defined. And by changing out these connectors and then mating them, it's a math term, right? by mating these two pieces to form this boundary on the limit set, you get new property sets. With the new property sets, you get new interactions. So you can control how those look, and you can control then the topologies of that system. Now, topology is referred to in mathematics, particularly by the topologist, as being the soul of mathematics, because it tells you what your potential is. It doesn't tell you what you are doing, it tells you what your potential of doing. Because in the most abstract sense, it's really the roots or the eigenvalues of a particular equation. So if I give you a matrix, I tell you these are going to be a lot of roots, it tells you what you're going to be capable of doing. So if you thought of the different colors as holes or poles, I can have different behaviors coming out of the same sphere, the same piece of space-time. So, to bring it down into concrete terms, that's what we're looking at. You see a nucleus of an atom, you see an electron, and if the light were good enough, you would see a fractal system on the inside. So that when the electron transitions from an outer shell into an inner shell, it interrupts this system. And when it interrupts it, you can see that energetically with spectroscopic methods, and you can detect it in the bulk as it changes physical property. It's really that simple. Key word is the space is empty. Right? Oops. They don't let me in the lab, and they don't let me program the slides. All right. So I'm doing this for a pretty general audience, and we begin with the relationship between matter and light, right? Einstein's principle of equivalence, right? Those were his original words, between mass and energy. And notice how he wrote it. Mass is equal to energy, so by definition, the independent terms are over here. We write it this way because it's more compact and probably because it was saved on ink, right? Literally, right? So is the presence of light a coincidence? Right? Why C? You know, there are embeddings in C that demand the functionality of light. Right? We know the light's unique. We know the speed's unique. Well, we already said that the propagation properties of light determine the metric structure. So we view space in a more fractal sense. And we ask ourselves, does C take its value from that limit set? So a path integral now of that system. And as a consequence, let me go back here. As a consequence, oh, I can't speed that up. As a consequence, you saw two things, C and C bar, right? That's what we're trying to prove. That C comes from the downside of the traverse, and C bar comes here. And that when you match them, you get C squared. That's what you see. That's what you measure. Right? Caught it at the end. If it was more competent, I could speed it up, but I don't know how to do that. So when you come down and you start thinking of light literally as a boundary, right? Because if you look at this equation, there's, oh, back this up. If you look at this equation, you know in a math term it's a scalar, right? That's what it is, right? So transformation operates a scalar. But from a physical term, you've just gone from something that's viewed as continuous to something that's discrete. Well, that's kind of odd. You've gone from something that looks like a particle to something that looks like a wave. That's kind of odd. So you start coming down. Is it a function? Is it really a scalar? If it's a scalar, does it index the system? Right? Is it what the mathematicians call functional, so that you can take a packet of information and then move it under a particular transform. So, knotted forms of light. I like nature a lot. All right? This is where I think we're headed. Right? And you as artists know this to be true. You have an idea in your head, and then eventually you reduce it to paper, and sometimes the paper over to a piece of equipment. So imagination is the beginning, and then eventually you create what you imagine. Okay. So the question is, how does nature use light? Because we see it everywhere. We see it as a generator, and we see it as a consequence. And we see coherent structures, long-range ordered coherent structures. How does it form those? Well, there's a set of math, in my opinion, on how it's formed, right? And the key on that math, as you already know, is going to be light. Because it has a bunch of structures in it that the universe has that I never knew were that way. So, this is the inverse problem. So a mathematician, there's two ways you talk to them. You tell them what you want, you give them a differential equation, you tell them to solve it. And you tell them, I know everything about it, but I don't know the differential equation. And if you tell them it's a feedback system or a retrosynthetic system, they look at you the same way you look at me. And if I tell them there's an inverse problem, they say, oh, I understand that problem really well. And that's what it is here. We're trying to deduce the natural geometry of light based on understanding which functions and which symmetries we're using to try to tease it out of it. So we have a bunch of definitions, but this is the key. I just use it. It's the bromine rings. The key is that if you cut one of the rings, all of them go away. And there's an identity function that goes with the system. So I have some definitions. I have how do we create new mixed forms, and then I have how you access it. Right? You access it through a set of relationships that I just use shorthand as the bromine rings. Right? And then I have, you may not know this. Many physicists believe that matter is just folded space-time. Right? So if I control the boundary, I control how it's folded. So if I think that origami is a good example, it's a great example. So I need a condition for folding and how you do that. And then I need a condition for aggregation. Right? And I don't know what these conditions are yet. I know what equations work for me. And I think, this is way too dumbed down right now, but I think we're going to find that there's something here, which I haven't been able to express yet, that is conserved. There's a symmetry there. I know that to be true. And I don't know if it's topological torsion or tension. I'm still working on that piece. But I know that that's the way of going from something really small, like an electron, to a bulk effect. Right? All through the aggregation. That's why there's this here. But you have the forms, you match them, you have a set of symmetries, you fold it, and then you aggregate. Set of geometries. Not really a set of math, it's a set of geometries. Well, if that's true, what do you think you can change? Pretty much everything here. Because light plays the central role in all of these. So you should be able to change your observables coming out of Maxwell, change your observables out of Schrodinger, change your thermodynamics, change your gravitational fields. You should be able to change a lot. Now, how do you know we're not smoking dope? Right? Light injection of a physical property. So there's two things that people want to see initially. First, they like a good idea, then they like to have some sort of proof. And then after you have some sort of proof, they want to know whether it's repeatable. And then after you tell them it's repeatable, they want to know whether you can control it. And then after you control it, they want to know whether it has great commercial utility. And if it has great commercial utility, it's no longer a new idea. So that's sort of where we go, right? So here we've taken pure copper, 99.95% pure by weight, which quantum mechanics says cannot be ferromagnetic. Impossible. There's only 5 known elements that are going to be ferromagnetic. And this is a 316 ionate immium boron magnet, a super magnet. It's not the kind you have in your refrigerator typically. Not even in my house. I had them in my house until I realized that if you eat 2 of them, you'll kill your little kids. So I got rid of them. Because they get bound up. Right? So here you go, right? Notice first, there's 2 different pieces of copper. Different experiments. Different size. Still pure copper, but notice this one that came out of one workup, this came out of a different workup. So we've gone from a 3/6-inch magnet to a 1/2-inch magnet to a 1-inch magnet. So not only have we been able to control it, reproduce it, get control over certain pieces of it, we've been able to move it around, and we've been able to move it around with visible light. very specific frequencies of visible light. How can that be? Anybody play the guitar here? Everybody's ever listened to a guitar. Okay, so if you put a capo on it, put a capo, I think it's right? Capo? Put a capo on a guitar, it changes all the tunes, right? Changes your effect of the music you're listening to. Let me show you how you do that, how light does that here. It's changing out the connector. Oops. Oh, I didn't put the other one in. I have the same slide here for copper, for cobalt, making it ferromagnetically attract sulfur. I can show it to you at the end. Right? So, how we do that is when you change out the connectors, you get to change out the knot. So this is just like a knot in a marine knot. Right? If you looked at the physics of knots, the work potential is defined by what type of knot it is. That has to do with overlaps and tensions and those sorts of things. And what type of braid it is. Is it a hemp rope? Is it a nylon rope? Is it a composite? Those sorts of things. So we have a tori here and a Hoffer vibration, which is a topological view of the electromagnetic spectrum. This is the quantum view. The physicists call it a quantum bagel. That's what we think we do. Right? It's interchanging of those two. And what we do is we orbit a group around there, and we space fill it. When we space fill it, we change electrodynamic interaction, we change properties in principle. So if I can change out the tiling here sequence, just like on your bathroom floor and some of the exotics that you see, you can get really, really cool patterns. Those patterns just represent different electrodynamic interactions. And all physics knows the physical property is a result of changing electrodynamic interactions. Actually, what they know is that physical properties are the result of electrodynamic interactions. If you want to change the property, you change the interaction. So that's what we do. We have your animation, we have one half of the sphere, and the other half of the sphere, or the traverse. We're trying to build out a new knot, so this is where the knot is. If we inverted it, that would be where your light cone is. And these are the energies going into the system. So if I could change this out by passing in a new connector type, I can change out how this knot is going to arrange. I can change out those interactions. So these are simple examples where you had the same grid and you just reorientate it to get a different symmetric structure. Just think of that structure think of that as a set of magnets on a field. You're going to get different patterns out of that. Those patterns are going to be your physical properties. And we just tile it. So we go back to fractal sets, and we go back to tiling. So mass gets back in the thick of it. That's the boundary that we're trying to create. We have a new structure at each one of these points that are recursive. We know how to match them. We already had that folded points from before. And what we're going to then do is we're going to bring that in. We're going to create a new guest structure, which we're going to tile. So I'm not claiming I'm creating new copper. I'm claiming the copper in every other atom that already has this potential. I think that biology uses it all the time, which is why we have a hard time replicating a lot of stuff they do. And then it just tiles it around the system. So, more space-filling examples. Who was it? Hoya. Hoya proved, brilliant mathematician. Hoya proved that if you're on a two-dimensional surface, you can enumerate and always find a solution. And he discovered that theorem when he had a graduate student who was out at Stanford, a graduate student was a gardener. His graduate student had a girlfriend. And Hoya used to go through the garden and he kept running into him. Well, the student didn't want to see it, so he kept moving, right? And Hoya couldn't understand why he kept running into these people. And then he went out and proved that as long as he's enumerating 2D, he's always going to find it. Not true in 3D. So when I'm convinced that I'm on a two-dimensional surface, I will enumerate. And when I think I'm not, it's all feed-forward math. So what we have here is a traverse where I'm trying to build up this boundary which leads me to a knot. And I want to see if that's right, right? Because these are recursive structures. So as I tighten this, tighten my interactions, the singularity of those interactions, do I improve my effect? That's the general idea. So these space-filling curves are the same ones you saw before. There's tailoring, you grow them, tailoring, you grow them. So eventually there's only one boundary, one orbit that this knot of this group will see. And the triangle is just a representation of what we're going to tie over that tori. Right? So here you have a piece of cobalt. It's attracting iron filings, right? Fairly interesting if you've never magnetized it, right? But here you have the same piece of cobalt attracting sulfur. Very interesting unless you glued it on, right? You didn't. No, I didn't. Nor any other form of adhesion. Now what I do is all I've done is a new sequence of lights to increase the density here, to tighten up that orbit. And as that orbit interacts, it tightens up the interaction. So if someone once told me, what's the difference between a tire on a Kia and a tire on a Rolls-Royce? Other than the cost. It's all in the width of the probability distribution of molecular weights. So as that becomes narrower, your response is going to become more predictable. That's what we're doing here. We're narrowing that boundary so that the response becomes more predictable. And these are all done at room temperature with light. Just a simple, not simple really, but just a light sequence. Right? The light sequence. This dimension is, well, it's about like that, right? 3.5 inches, I don't know how many centimeters. And this is 37% of the surface area, and that thickness is a 1/4 inch, 1/4 to 3/8 of an inch thick. And this is pure sulfur. And since you know how to, what a capo does to a guitar, if I mixed another element in with this sulfur, I should be able to modulate that behavior. Because that other element is going to modify this energy coming into the knot. So, implications and applications from the subatomic to the macroscopic. I start with a quote from the beginning. Right? New materials means new forms, gotta use it according to the nature. Right? Nature seems to be doing it all the time. It's a struggle, though, for me, right? And I love this quote that we had on reinforced concrete. Because you read that book, it's the greatest invention since sliced bread. But he really comes down to it's a fluidity. And you look at these structures, I mean, these are real, unbelievably impressive, in my opinion. So what we want to do is we want to create new knots by changing out the connectors. So when we do that, this is an atom, right? And if you go to the National Institute of Bureau of Standards, you go to standard physics, they're going to tell you the spacing in atoms is known and fixed. In fact, they call it a physical constant because it's unique to copper. And that's why we can tell copper with spectroscopic equipment from other materials. And they know these numbers within 1 electron volt. So the lights coming out of here are 1 to 3 electron volts. Same thing here. These are in kilo electron volts. Right? So the tolerances here in terms of how much they move is extraordinarily well classified. And these are the inner core electrons. So if you use the old Bohr model of a baseball as the nucleus, this is the first core. The chemists would call it in high school the S shell. Physicists would call it the K. And then you knock an electron out, one transitions down, has to go to lower energy, you measure that photon as it drops. And that's what you see here, right? So we're looking with X-rays at what does the interior spectrographic signature look like? What do these atoms look like on the interior of the magnetic region versus outside the magnetic region? And we see very nice overlaps, and then we see humps. It shouldn't be there. And those humps can be moved with light, and they can move with time. And that's what we're showing here. We have a spot that has no magnetism to iron or to a magnet, a spot that has attraction to iron and a magnet, and a spot that only has an attraction to iron. All right? So one of the big things is, well, how do you know it's not iron embedded in here? Well, if you magnetize it, and I'll pick it up as a Gauss read. If it's impregnated iron, then it shouldn't move and it shouldn't go away. Well, we can make it do all those things. And that's what you see here 22 hours later, that they flip. That the red is greater than the black here. Now the black is greater than the red. And after 250 hours, it's equivalent. And if you look at those peaks, not only is the intensity changing, because it's well known that in pure elements, if the inner core transitions out with this probability, the second one is going to come out with this, and those ratios are known constants for pure elements. The intensity of the peaks are changing in time, the relative intensities are changing, and they're shifting, right? Greater than plus or minus 1 EV in this particular case. Sometimes a lot more. Here's a more graphic example. Here you have a piece of copper. It's a slice off of 100 pounds. So 100 pounds of copper is about that much in diameter, about that deep. Right? This happens to be a cylinder. And we take a map over the surface, and the length of this map is probably 2.5 inches long and 1.25 inches wide, would be my guess. All right? And we're measuring areas where the instrument thinks we have iron. And the reason I say the instrument thinks it has iron is that the way all these work, these sense of physical constants, being good engineers, we had a lookup table, and if the spectra comes within a certain sigma of it, we label it as iron. And so you actually have to go back and look at the spectra to discern whether or not it actually is iron. Right? And what you have is this is the Artex image of it. That's an energy dispersive piece of X-ray where you get the full spectrum. And here you have this map overlaid, and you have the magnetic spots. It actually is a magnet right here. Here you have iron filings or iron powder on a magnetic spot, and you have a system that goes away. And you shine, well, I did do it that way. Had a bunch of laser pointers and flashlights. It's a very particular design. And you could shine them on with a sequence and you would come back.
But just to be clear, that is pure copper.
Pure, 99.95% by weight pure copper.
But if you look at
the spectrum, it isn't. So, all we're doing, we're coming right back to knots, right? We want to change out the knotted structure, change out the interactions. It's that simple. Ooh, you've seen these. So the question then is a particle in the wave-particle duality just a knot? Right? Just a knot between these fields. And then what you're really getting is the densification. You're following a boundary there. Right? I obviously have a strong opinion on that. Right? So if we use an example from nature, what we want to do, if I shine, I should have had that. I can find this slide. So I take this magnetic spot, and I shine a particular type of light on it, and I get a ferromagnetic activity. And then I change out the light, and now I get a diamagnetic activity, something totally different and unexpected, just by changing out the lights. So I said, all right, where does nature do this? If this is a reasonable paradigm, I know two things. Right? I know that if I constrain the knot, if I constrain matter well enough, I'm going to force back what these arrangements have to do. Right? Mathematician Thurston proved that. Right? He would call this the knot, and the orange stuff the complement. The complement in free space uniquely defines the knot. Right? So I can push those back and forth. So in looking at nature, is there an easy way of forcing the knot to have different properties, or just passing a new conductor? And everybody in this room is familiar with this example. Carbon, right? In my opinion, what you're really doing there you've arranged your carbon atoms into a particular knotted configuration, which enforce a new geodesic in the complement, which leads to a particular set of connections. Diamond is the same material. Look at how much these physical properties change. I mean, it's massive in terms of hardness, in terms of conductivity, electrical, and other, in terms of optical transmission. And now you go to nanotubes, again, the same thing, right? A fractal type of energy bond, very different once again. My assertion is you could do that with carbon and polyethylene and the like, just by changing out the chemical. And here's an example, right? You're taking copper, it's 12 years old, and it's effectively non-reactive to oxygen. I can also take that copper and shine on light and make it dissolve in bleach, like that. So they're not very good for copper pipes. And the way I did that is knowing this structure. You know, it's like designing a homework group, right? You have a group, the first thing is, well, in my department, you wanted people that are really smart, and then you wanted people you could work with, right? You wanted both of those. In my department, when I graduated from, they liked you to work in groups so you wouldn't kill each other. So what you do is you then graft on different pieces of that homework group into this massive problem, because there were probably only 2 people in the class who could solve it by themselves. Right? So there's an equation to do that. I look at a property in a piece of matter that I like, in this particular case, argon, and I said, argon isn't very reactive to oxygen, and I'd like that property on copper. So I'm going to create a new foliation, and I'm going to take the old property set in the new one, and I'm going to tile out a new boundary and graft it on the same way I would think of grafting a pear onto an apple tree, pear branch. So, okay, so path forward, my final slides. I come back and I say, it's the architect of matter, because it controls how, in my opinion, how matter folds. How space folds, and that's all really matter is. So here, when I use the word, I could change the light sequence and go to paramagnetic or diamagnetic. What that really means is minus, and what that really means is locus superconductivity. And that's what you have here at room temperature in pure copper. Here you have light that's been induced. You've injected a sequence so that cobalt paramagnetically attracts sulfur. Interesting trick. And here you have a time sequence where you're looking at how these interior orbitals are shifting. D is for days. So we would do a pre before the experiment and then a bunch of post, and then finally we do one around 28 days. And you notice it relaxes back, just like a hysteresis. So all of them are induced by light, and it's my opinion that light's a massive boundary of space-time. Since that doesn't mean anything to anybody, I improve that to say it's a geometry of space-time. I mean, that's really where we're going. We're trying to establish, not only is it geometry, it's a natural geometry, which means I can do a lot of calculations forward and back. I mean, you people are familiar with 3D printing, right? Before you had Euclidean geometry, back when nobody was, and you could figure out plots of lines and areas and volumes. Now you put those into a program, and you create that same base, right? So you go both ways. That's the goal. That's the idea. That means that the periodic table and the utility that you thought you used to have has now just been broadened and engineerable. We graphically represent it as cones going on the backside, but I think that's what really is happening. The topology is independent of energy. So some things, a good way of thinking about it is if you were a person of strong ethics, and I tell you not to go through the door, it doesn't matter whether there's a lock on it or not. You're not going to go through the door. And if you aren't, then they need bigger and bigger and bigger locks, right? That's energy. That's your barrier, right? Topology says, oh no, I'm going to change the ethics of this person. And with tunneling, what you're really doing in this paradigm is you're matching the wave functions from both sides, and you're matching it by creating a new boundary that it can commute across. So all in topological stability, just like the original rubber example, is independent of energy. I mean, yeah, you can blow the whole thing apart, But if you assume that you're going to keep it in your 3D existence, then all you need to do is have the right constraints so they can match. That's it. And you can do it with really low forms of energy. So the idea is, and I like this example, that's why I have it. The idea is the understanding all of this additional structure in light and in the empty space in an atom. It means that what you thought was a very limited orchestra is now a full orchestra. And by understanding the light's the geometry of that system, what you really have said is you understand the conductor of that orchestra. And now, knowing what I want unfolding, I can send the conductor sheet music. And with that sheet music, he's going to play different electrodynamic interactions and get new physical properties. With the potential of dynamic response, different types of habitable structures with very low energy transformations.
What do you mean by metal structures?
I was hoping a student was going to answer that. You have functions, and you have functions that design functions. So I think of, we're very driven by the global challenges and sustainability. What are you going to put in your building to make it more sustainable? What are you going to put in the building so that it can be self-policing? What are you going to put in the building so that it can adapt to the resident in something that's way beyond Bill Gates in terms of music and pictures, in terms of not just environmental controls, production of materials that you want. Which is why I always bring the space lab in, because it drives my thinking. I don't think in this dimension. But it drives my thinking here where you have real estate requirements, you have a lot of different forms of energy available to you. What can you now do in that type of system? And it's one of the things probably previously funding. So what have you just heard? All of physics is based on really two things. A clock and a ruler. That's it. A clock and a ruler. Right? And normally the ruler is an energy ruler. Right? And those are invariant. And with that, we've done massive things which are really cool. Right? Now what I've shown you is that I can change that space, which means I can change a clock and ruler. So the example that I give is you've just discovered the number line, the integers. It's an amazing set of numbers. And now I add in irrational numbers, add in transcendental numbers. Now there's a lot more utility. I mean, pi has a lot of utility, right, compared to 3. And from those, we can long-range order materials. This is at the with the atomic force microscope, scanning electron microscope, and atomic microscope, TEM. So very, very, these are recursive structures all the way down.
It's like the graphite.
Pardon?
It's like the graphite on the another material.
Yes, in 100 pounds. Right? The partial Meissner effect, the sulfur, the changing. This centroid is changing on the system. Here's the copper, the 100-pound slice, so that dimension is about 8 inches. Notice it's regional selective. Right? You've got 4 quadrants here. And one of those quadrants, we activate the end of this, and it densifies, adiabatically densifies. So copper is heavier than the copper we looked at in the book. And if you flip that over, you have pits right at the end, which are highly reactive to 2 things. Well, really, 2 things. To a light sequence bleach water system. So, I think this is on the last slide. Looking at the global challenges and how you as cognitive architects can address some of them, right? I mean, this is really where we're going, right? These are the big ones, right? I think they're even here, right? How do you put those in to the system? And what I'd argue is going to demand a new way of thinking, a new paradigm. You have the whole idea of space and growth, and now we can expand that view of what you went with in space. We can do the same thing for housing and getting not only into structures which are more accessible, lighter structures, more durable structures, and structures that make it more suited for climate control in a wide range of regions. Right? I was reading the other day that the crow or the raven is the only species that can live pretty much anywhere on the planet other than underwater. So it can live on the polar ice caps, it can live on the top of Mount Everest, it can live in the Sahara. Pretty interesting system when you start talking about metastructures. There's a great challenge. Right? Carbon, right? I'm not proposing putting trees there, but I am proposing there might be new ways that you could think of integrating the systems. Because one thing's for certain, we are off the cliff in terms of global warming without a way of reintegrating it. And then energy. I think we're going to find that there's some very new ways of addressing the energy equation. It doesn't involve hydrocarbons. It doesn't involve solar cells the way you classically think of it. And that's it.
I think you get that. This is he thinks very, very